Classes in Statistical Mechanics. Lectures by Professor George Phillies, based on his book, Elementary Lectures in Statistical Mechanics, Springer Verlag, 2000. And today, this lecture is so far so good. Okay, now we come to the last bit, which is averages. And so we imagine you have the misfortune to be assigned a conference section of 3 freshman students, and you are teaching them. And their averages on their scores on the first exam were 100, 50, and 0. And we ask, what was the average score of the 3 students? Well, it's 100 plus 50 plus 0 over 3. And that is an introduction to long division. And if you think back to like 5th grade, you were probably told about averaging grades. And then if we talk about one student, and so the student on the first exam got a 0, and on the second exam got a 0, and on the third exam got a 4, and on the homework, which totaled to 100 points, got a 26, and on the 50 points worth of lab got a 50. This is not encouraging. Yes? And if we said all of these are equally important, if we said these are all equally important, we might divide by 5.
80 divided by 5 is...
Well, you could, if you said each of these were equally important. But you could say something else. You could say exam number 1 will be worth 100%. And exam number 2 will be worth 100%. And exam number 3 is scored out of 100, and so the weight of exam number 3 is 100. And then the homework grades are only worth 50%, so we'll multiply the homework grades by 50 instead of 100. And the lab grades are worth 50%. So we'll multiply the lab grades by 50, and we add all of these up. But this isn't an average yet because I have to divide by something. And what I divide by is 100 plus 100 plus 100 plus 50 plus 50. That is, I go in there and I divide by the sum of all of the weights. Does this work correctly? Yes. If the person got a 100 on everything, and you plug in 100 for the 3 exam scores in the lab and the homework, and do the math, the average will come out to be 100. And if they got 50 on everything, the average will be 50, because this thing in the denominator divides out all of the weights. And so the weight, this piece in the denominator, the normalizing factor is there, so that when you average everything together, you get the appropriate average. And if you say if the person got a 1 on everything, God knows this happens, the average grade of all of the grades is a 1. I'm now going to write this down symbolically. We have some variable a, and we take some number of samples of the variable a. And we will use the subscript j to label the individual samples. So a is the value in sample j. And we add up over all capital N times, we did the average. And the statistical weight for each of these is W. That's how important each of those A's is in the average. So each time up here we multiply W by A. And then we must divide by the sum of all of the weights. And this is a weighted average. I mean, you sometimes do weighted averages when you're doing experiments. And there are the days the experiment was clearly running very well, and you weight those points better. And there was the day the experiment was not running well, and maybe give that one a lower statistical weight. And there was the day the professor walked in and ran the equipment, which he designed himself, and perhaps you give that a statistical weight of 4 rather than 1, unless you observed him when the visitors came in, lecturing to the visitors on the equipment while pointing at your auto transmission, which you were in the middle of disassembling to repair, in which case you give them a statistical weight of, say, 0. And so you average all of these things together, and that is a statistical weight. And that is an average, and it is a weighted average. Now, in the original cases, we were saying we had values for W, but in general, for example, W could be a value, how shall we put it? W could be a function of J. Let's take a simple case. Where'd they go? They're hiding in here. These are dice. And if we roll the dice, they're icosahedral dice. They give us a number between 1 and 20, like 4 or 18. Yes? And so if I ask you, what is the average value of rolling the dice? This is a D20. If I roll the D20 many times, what is the average numerical value of the die roll? Well, the numbers go from 1 to 20, and if you do the calculation and say it's equally likely to come up each way, you will calculate that the average die roll value is 10.5. Yes? On the other hand, I could say, gee, this is a somewhat unusual reason for using the dice, and the score is not the 4 or the 18, it is the square. So if you roll a 4, it counts as 16. If you roll a 10, it counts as 100. If you roll a 20, it counts as 400. And if you ask, what is the average value of the square, you do the math, and you will come out with some average value for J quantity squared. Assuming the die is an honest die that gives all rolls evenly, as opposed to a cheater's die, which has little lead pellets inside one side, so some dice come up more than others. Some dice sides, I should say. And so if you say this generates a random number, and we'd like to know what the average of a large number of rolls is, you can imagine calculating it. Except I am right at the edge of the last transformation of that. We can imagine calculating it. There are two sorts of ways to do the average. And I asked you, what is the average of rolling this die many times? And one thing you could do is wander over to the local comic book store and buy, say, 100 of these and a big bucket. And fill the bucket with the dice and roll it and count everything. And repeat and count everything. And you roll the dice 10 or 100,000 times. And you then calculate the average from your actual experimental results. This is known as an operational average because you actually did the operation. And one of the homework problems involves actually doing this. Except what I tell you to do is do the rolls, compute the average of having rolled it the dice 10 times, 100 times, 200 times, and look at what happens to the average roll as time goes on. And what will happen is that as time goes on, if I say roll those things, maybe if I just roll one die, the number can get any number once. But if I roll 10,000 of them and take the average will be pretty close to 10.5. And if I roll them 1,000,000 times, the average will probably be much closer to 10.5. It is not guaranteed that it will be closer to 10.5, and maybe you'll have bad luck and you will have rolled 1,000,000 20s. But that's not very likely. That's still an operational average, though. And now we will take the transition. And the transition is from an operational average, where you actually grab the dice and roll them and keep rolling them, to an ideal average. And in the ideal average, you say, this is a well-made D20. You see it has little purple flecks in it. Can't be better made than that. And because it is a well-made D20, the likelihood of each side coming up is the same. And so we'll say each side has a statistical weight, Wj, which is the same as for each of the other sides. We say the statistical weight is 1. It does not matter what you say the statistical weight is, except, the die can come out 20 different ways, so j can come from 1 to 20. The value of the roll, if we say roll of 4, is 4. And the statistical weight is a constant, the same for all of the sides. And then down here, we put in all of the constants. It's the same constant each time, and add them up. And I have now done the same thing as rolling the dice 1,000,000 or 1,000,000,000,000 times and taking the average, except I've thrown out the fluke possibility. Yeah, I rolled the dice 1,000,000,000 times. I rolled 1 1,000,000,000 times. Well, we're going to throw out those flukes, and we're going to look at the ideal average, and the ideal average says those funny things don't happen in a way that would cause us problems. And so I can calculate the average value of the die roll as W times 1 plus W times 2 plus W times 3, etc., up to W, the same W for all of them, times 20. This is one of the homework problems I'm going to assign, though I'm only going to have you do it for one side, one type of dice. So in any event, you are going to go in, you're going to say, yeah, you could roll the dice lots of times and take an operational average, but there is also this ideal approach to taking an average. Which of you have had some exposure to statistics along the way?
Probability.
That's sort of it, a little bit. When the mathematicians teach statistics, there is one minor difference between what I just said and what you probably heard in probability class. That is, in probability class, if they talked about these, they would say Wj was 1/20th. And therefore, the sum of the Wj's is 1. And that is because mathematicians talked about what they call normalized probabilities, where the sum of all of the probabilities is 1. In statistical mechanics, we talk about non-normalized probabilities, and the reason we do that is the sum of the statistical weights has a physical meaning. And if you change it, the physical meaning changes and you have the wrong physical meaning.